Hey everybody, how about this crazy weather? It's been kind of nice to be iced in. I hope you're enjoying yourself and your time off. I know I am. Doesn't mean I've stopped working, but it sure is nice to kind of be home at the house. And I bet you feel probably pretty much the same way too. I wanted to kind of visit with just the BC students right now. So if you're an AB student, you just want to put this on hold and maybe shut me down. But if you're a BC student, I just wanted to kind of visit with you just a second and let you know that I'm very thankful for Camtasia and this platform and this opportunity that allows us to not get far behind. This recording, etc. stuff is going to allow us to keep up where we need to be so that we're prepared and we're still successful in May when it comes time for the AP test. So I'm real thankful, and I thank you for letting me intrude upon your days off from school and allow us to kind of continue our studies in somewhat of a good way here. I just want to kind of point out to you guys, you BC students, that we were in the last four videos probably, we were finding antiderivatives. We were integrating. We were given a function and asked to find what its antiderivative is. And in this video, I just kind of preface it and say with you guys that we're going to take a 180-degree turn here, and we're not going to find antiderivatives today. What we're going to do is we're going to actually approximate the area between two graphs, two equations. And there is a big connection, I just want you to know, there is a big connection with finding antiderivatives and area. And that will be revealed in the next lesson, the next tutorial. So just kind of be patient, just kind of go with the flow, and let's see how we're going to approximate area, and in the next few days we'll put it all together and see where we're at. As an example of what we have been doing, if we wanted to consider this integral of this function x squared minus 6x plus 13, based on our studies so far, we would know that we would take the integrand and find the antiderivative for each of these terms. Well, let's put some vocab to what we've been doing. All right, this is called an indefinite integral. An indefinite integral. And you guys don't have to write this down. If you just want to watch, I'm just going to give you some background information before we do actually start taking new notes. So this is called an indefinite integral. And so when we see something like this, what we do is we do find the antiderivative. Okay, and just know that the answer is a function. And you knew that. The answer is a function. Sorry it's so sloppy. My hand must be frozen. All right. What we're moving towards after today's lesson is we're trying to look at what difference does this have for us. That is, if I put limits, I call these limits, if I put limits at the bottom and the top of the integral symbol, well, how does that look differently than what we did previous? Okay, notice the difference between this expression and this expression right here. Here we're told through the symbols to find an indefinite integral. We're told to find an antiderivative. Okay, well what does it mean for us when we have the same situation, but now we have a lower limit and we have an upper limit, is what we call it. What does that mean? Well, this is no longer an indefinite integral, it's a definite integral. Alright, so this is a definite integral. So what does our answer look like? Well, our answer is actually a value. When we put limits on our integral symbol, we're looking for a numeric value. Our answer is a value. Okay, well what does it represent graphically? Well, we'll look at that here in just a second, but I just wanted you to know the difference between an indefinite integral and a definite integral. And they direct us to do two different things, I guess you could say. Here we're going to find an antiderivative. Here we're actually going to find an antiderivative, but we do something further with that antiderivative because of these limits right here. So again, don't worry about writing any of this down. This is just some background about where we're moving to. All right. So the title of the notes are Rectangular Approximation Method, RAM, Riemann Sums. As we go through our example, we'll see more about this title as we go through and work the problem out. All right, we're asked in this example to approximate the value of the integral x squared minus 6x plus 13 from -1 to 5 using a left RAM with 6 subdivisions. So just trying to decode what we have here and what we're asked to do. So just some background. This 6 right here indicates to us how we want to partition, if you will, divide up the x values from -1 to 5. So one thing you need to know here is that this -1 is our lower bound, our lower x bound. We call that a. Okay, and this upper limit right here, this 5, is called our upper bound, or 5. So both these are x values. This goes from, this graph we're interested in, from x equals -1 to x equals 5. And how we're going to approximate the region between this curve and the x-axis is we're going to be using rectangles on the left side, and we're going to be using 6 of them. We're going to use 6 rectangles to approximate the value of this integral. So I think at this point it would be helpful to get a picture of what we're doing. As you can see, I've created a grid here. I've created a grid of x values from -1 to 5 based on our lower and upper limit, our a and b values, if you will. And what I did was I took the time to plot certain points that are on this quadratic right here by taking -1, 0, 1, 2, 3, 4, and 5, and one at a time replacing them into the function and finding the functional values. So you can kind of see that this is the parabola that we're working with. We don't want the entire parabola because now we have a definite beginning and a definite ending place for our parabola. Alright, so this is going to be the tricky place for me, is to try and connect these points, but I know you can do it a little bit better than I can with this pen. So let's just consider the parabola that goes through -120. Notice the partition along the x-axis and the y-axis. I believe this point, or this functional value, would be 0, 13. And that makes sense. If x is 0, my output is 13. Okay, and then I found all these other functional values by replacing them into the function. Okay. Alright, and so the graph does continue off that way, but again, all we're interested in is the x values from -1 to 5, from a to b. Alright, so I'm going to draw vertical lines at the a and b values. So from -1 up to this functional value, and then from 5 up to this functional value. So if you can kind of see the bounded region here, we're really looking at what the space is between the quadratic and the x-axis, okay, from -1 to 5. All right, if you think about it, we're going to be interested in finding the value of this integral, which means we're going to be interested in finding the area in this space right here. But based on our past background, we don't have a geometric formula to find that area. That's not a known geometric shape. So the best that we can do right now, before we get too much further into this lesson, is we can approximate this region. So we approximate it by using rectangles, because rectangles are easy to calculate, at least the area is. All right. So let's pay attention to a couple of things. I want to do 6 subdivisions, that's what this directs me to do, from -1 to 5. So how wide will each of these rectangles that I'm going to be using, how wide will they be? Okay, well, let's find out what the delta x, the width of each of these rectangles, are going to be. So delta x is going to be b minus a, the difference of your two x values, divided by the number of rectangles. So in this example, b is 5, a is -1, and we're directed to inscribe 6 rectangles of equal length. So perform the calculations, we get 1. So delta x equals 1. The width of all of our rectangles are going to be 1. They're equally spaced in this particular problem. So that's the width. Alright, so let's get some notation here. So in the coming days, we're going to actually be able to find the exact area that's in this region by using calculus and using what we had learned before, indefinite integrals. But right now all we can do is approximate the value here by using a left ram, L for left. We're also going to be finding right rams and midpoint rams as well. Okay, so this is going to be an approximate, and I'm going to put equals here. Alright, so let's get an idea of what we're doing over here on this picture. Alright, I'm going to start from the left, far left, and move to the right, and I'm going to inscribe rectangles of equal width. So first thing I have to notice is that I have a width of 1. So starting with -1, I'm going to travel as far as, horizontally, as far as 0. So what I want you to do is think of that as the bottom of your rectangle. That's the bottom of your rectangle. That's how wide it is. It's 1. The only thing left for me to do is find out how high my rectangle is so that I can multiply my base times my height and get an approximate area. Alright, because we're asked to find a left ram, once you establish what your partition is down here, go to the left side of it and then find the curve. Well, the curve happens to be up here at this functional value. So what you've just done is you've created 2 sides of a rectangle. We need 2 more sides, obviously. We only have 2. We have the bottom and the left side. So because it's a left ram, I'm going to let the function on the left side determine the height of my rectangle. I'm going to travel and put a top on my rectangle. So I've got this bottom, so I'm going to travel far enough to where I've completed a rectangle. So now I've got 3 sides, and all that's left for me to do is drop down right here, and I can now see that this is my inscribed left rectangle. Well, we can come down here and we can find the area in that rectangle. Well, its base is 1 and its height is the functional value on the left side of this partition at -1. So it's going to be the functional value at -1. We'll come back and put the values in just a minute. Plus, that's 1 of 6. I need to find the area in 5 more rectangles, add them together, and that's going to be an approximate. As you can see right now that the area in the rectangle is an over approximate of the area from the curve to the x-axis because the curve is decreasing and I'm using a left ram. And all that means is my rectangle will fall above my function. Alright, let's move on and see if we can inscribe another rectangle. Alright, we ended up here at 0, so now that becomes my beginning point from 0 to 1. That's the bottom of the next rectangle. So I have 1 side, I need 3 more. Well, we're doing a left ram. Choose the left side, 0, go up to the curve, stop when you get there. Okay, this is now going to be the left side. Change colors here. This is now going to be the left side, okay, of my next rectangle. Alright, let's put a top on this rectangle. Travel as far as you need to so you line up vertically with the other end point of your rectangle. Stop there, drop down. Okay, so this right here, okay, this area is an approximate of the area from the curve to the x-axis. So what does that look like as far as the area? Well, it's still 1 wide, the rectangle is, times, now how tall is that? Well, the functional value in here is 0, 0. So it's going to be easy enough because we have an equation, we can go back and evaluate the equation. Alright, let's continue. Alright, let's go back to this color here. Okay, the next rectangle is going to begin at 1 and end at 2. It's a left rectangle, so on the left side at 1, go up to the curve, stop when you get there, put a top on your rectangle, drop down. You can still see that this area right here that we're finding is an over approximate because my function's decreasing and I'm using a left ram. Okay, so what's the area in that blue rectangle? Well, it's 1 times the functional value at 1. And I think you see where this is going, but we'll go ahead and complete this one by inscribing all the rectangles. Okay. Alright, we need another rectangle. We need a 4th one. So we start at 2, we end at 3. It's a left rectangle. We go up to the curve, find it. Okay, travel over, complete the rectangle, and come down. So the expression that represents the area in that rectangle would be 1 for the base and the functional value at 2. Okay. Notice that we still have an over approximation, and that's because the function is decreasing with the left ram. Okay, let's inscribe the next rectangle. It starts at 3, it ends at 4. Now notice you go up to the curve and you draw over. That rectangle falls under the curve because now the curve starts to increase and we're doing left rectangles. So let's find an expression that represents the area in that rectangle. So it's 1 wide and its height of the rectangle is the y value of that point. So that's what, f of 3? And we have 1 more. Okay, for the last rectangle, we start at 4, we conclude at 5. At 4 on the left side, we go up to the curve. It's an under approximation 2 because the function's increasing with the left ram. That kind of balances out this extra area right here. An expression that represents that area is going to be 1 times the functional value at 4. right, let's perform the computations to get an approximate value of the area. So this is 1 times, I believe that was 20, plus 1 times f of 0 is 13, plus 1 times the functional value here when I plug 1 into the function is, it appears to be 8, plus the next rectangle is 1 wide times the functional value next, I believe, is 5, plus 1 times the functional value at 2, which is 4. And continuing to find the area. Let's see, we have 1, 2, 3, 4, 5. It appears to be 6 values, and that looks like what we need. Alright, just double checking here. Okay, the functional value is 20 there, 13 there. Functional value at 1 is 8, the functional value at 2 is 5, the functional value at 3 is 4, yep, and the functional value at 4 is 5. Alright, multiplying and adding all this together. This problem is kind of easy because our base is 1, so that makes the calculations easy. Alright, and summing all this, let's see, that would be 10, that would be 30, let's see, 30, that would be 43, 51. It appears that the approximate value of this integral is 55. Okay. So using left rectangles to approximate the region between a curve and the x-axis would be done something like this, using a left ram.